Now we can move to the last section of our presentation, which is how to derive the mass energy equivalence relation. Let me again stress that this energy, this relation, in its simplest form and in its relativistic form, cannot be derived in the current relativity. Many people don't understand this. Many physicists even believe that this equation is already built in the special theory of special relativity. Einstein himself tried this many times, starting from 1905, and many times later he published many papers. In the end, all these papers were discovered that he made some approximations unjustified. He was criticized by Max Planck, and he himself acknowledged this many times that even by the end of his life, he acknowledged very clearly that the theory of relativity, special or general, or the electromagnetic theory, is not enough. The principles are not enough to derive this equation. This equation, is of course correct. It has been proved experimentally, but there is so far no real direct derivation of it, exact derivation. There are some approximations, of course. And the reason why there is no possible derivation based on our current understanding is exactly because we are implicitly approximating the actual discrete geometry to the continuous geometry, where we believe that things coexist together. So here, this figure shows very clearly that if you are moving through the outer time, where you have here this x-axis as the momentum and this y-axis as the speed. So if you are moving in the outer time, where we are actually working, just like now we are moving in the outer time, therefore we need time to move, not instantly. We can't move instantly, and therefore we get this triangular integration, and therefore we get this kinetic energy that is half mv squared. So here we are moving outside at the speed of v, and therefore our momentum is mv and our speed is v, and therefore the total energy will be the square, the area of this triangle, which is equal to half mv squared. In order to reach this equation, we must suppose that the object moves from 0 to c instantly. And of course, this doesn't happen. It can't happen. The object cannot move from 0 to c at all, neither instantly, neither by acceleration. However, according to the duality of time theory, I am saying that the object, for example, when we have, for example, matter-antimatter annihilation, or when we have light absorption, when the C collapses to 0, when the light is absorbed. So this interaction is happening instantly in our time, but actually it cannot happen in the physical sense. It happens only in the inner time, where things have zero mass, and actually always the monad is bringing things into existence from void to vacuum, from 0 to C, or vice versa, from vacuum to void. So the monad is always doing this, is not moving in the outer time. Therefore, in the inner time, automatically we will get this square area, which is equal C by mc, so mc squared. Very easy. We don't actually now need to do anything further. But even though, I will show you now many derivations, exact derivations, but because now I am taking a long time, I will go through them very quickly, and I will leave this PowerPoint slides for you to download and see more derivations. Actually, I will leave even to you the full book of the duality of time and its consequence on general relativity and quantum mechanics. I will leave it for you to download free from my website, smonad, smonad.com, smonad, singlemonad.com. So let's now, in the remaining time, very quickly see some different derivations of this duality of time. But before that, let me stress to you that you may find on the internet some derivations, some people who claim that you derive this equation. However, these derivations, either they use approximation, or they use a famous equation m equal gamma m naught, and then they derive or they differentiate the mass, and this is actually again not correct, because you cannot get this equation from any simple principle. The equation m equal gamma m naught is equivalent to E equal m naught c square. So these are equivalent. If you derive one, you will get the other, and therefore it's like a round statement. So the basic idea, as you can see now, we are starting from classical mechanics, is we derive the energy, the work, for example. If you have any object and you want to move this object by a distance from 0 to x, so the energy or the work you get is equal F by dx. So if you do that, you will get V d mv. Therefore, you will get here this equation V squared dm plus mv dv. And actually, this is a really mysterious equation. Normally, in our classical mechanics, we consider m constant, and therefore we cross this and we say this is 0. However, this is true, but this actually here is the seed of supersymmetry, because here these two terms, the reason why this is 0 is because it's going in the opposite direction, in the orthogonal direction. And from here we will see that this is really the seed of supersymmetry even in classical mechanics. But now for the moment, let's suppose classically that dm is 0, and therefore we have mv dv. Now you can therefore integrate this. If you want to integrate it in a classical way, according to this arrow of time, you will get half mv square, and therefore this is a classical equation. However, if you want now to integrate on this arrow, on this inner time, okay, same thing here, but sorry, this not yet. It's actually the following slide. But then here, let me stress to you, as I already explained, that these two equations are equivalent, and you cannot rely on this equation to get this equation. You may find on the internet some derivations of this mass energy equivalence based on this equation. It's possible, but how do we get this equation? This equation is not available in the special theory of relativity. It's only supposed to be true based on the similar time dilation and length contraction. This equation looks the same. So these are possible to obtain through the Lorentz transformation, but this equation cannot be obtained. Only we suppose that it's there, and therefore from this we get this equation, or from this equation we can get this equation. These two equations are equivalent, and we cannot depend on one of them to derive the other. Also, these two equations, when we combine them together, we will be able to get the modern relativistic momentum energy relation, which is now maybe considered the true form of this equation. They are actually equivalent anyway. So this equation, or this equation, or this equation, these three equations are equivalent, and therefore deriving one of them means deriving the other, and therefore you cannot rely on that, otherwise you will be going through a round statement. So let's now see this slide. So as I said, if we now integrate over this inner time, and this integration actually is no more integration, it's actually summation, because you have only two states. So you sum over all the monads only from 0 to C, or only 0 and C. You don't have any medium between 0 and C. So the object only moves from non-existence to existence, or from void to vacuum, or vice versa, from vacuum to void. And therefore, if you sum over this, you will get m c squared, supposing that m is constant, and therefore dm equals 0, and therefore you put here dm equals 0. However, this supposition is actually not correct. Only it's correct in our world. Therefore, in reality, we have two terms, and each one is taking account, it's actually splitting. This symmetry is splitting. One is going in one dimension, and it's creating the same particles, the same MC, but in orthogonal direction, and therefore we get the same mass, the same energy, but we don't see it because it's supersymmetrical. But anyway, this maybe we will talk about it later. At least now for classically, if we suppose that dm is 0, then we get 0 plus mc square. So now this is the opposite side. If we suppose that the outside velocity is 0, and therefore the monads are going from 0 mass, from fermions, from bosons to fermions, then we are generating mass. As we said, we generate mass by moving by the monad moving from void to vacuum sequentially without going through the outside time, and therefore we are integrating only on the inner time. And therefore here it's the opposite case. It's actually this one will be 0 and this one will be c squared, because of course in this case you are moving only at the speed of light because you are moving in the inner level of time, so always v is c. So this c is constant, c squared is constant, and you integrate from 0 to m, you will get m. So it's again mc squared. So this is actually happening with this one that we have seen on the previous slide. They are happening together, but not on the same level of time, on two orthogonal dimensions, and therefore we have supersymmetry and splitting of this supersymmetry at every point of time. So in fact we have two masses, two energies, and therefore we have supersymmetry. Time is running out and I'm getting tired, so I will move a little bit faster. You can actually also, this is another method, you can find automatically the relativistic energy in the inner and outer time together by integrating this same equation at the same time, but however, you have to consider the inner time first and the outer time second, and therefore you will get this equation. Maybe you can review it and study it later. It's actually very simple and straightforward. Another method yet is by integrating also on the inner and outer time, but integrating the momentum. But remember now the momentum becomes complex, and therefore it has real and imaginary part. So you have to integrate on the real part first and the imaginary part. But in this case you have to put the complex form, which is indicated here by the complex number j, which is a hyperbolic. And therefore, if you do this integration, you will end up with this real and imaginary part. You can verify these equations. They are very easy to follow. But here you will get minus. So this minus here actually, in our equations now, in our current formulation of relativity, we see it as a plus. The reason of this is because we are considering in our normal life, we are considering space to be spherical, and therefore we are working with normal complex numbers. However, in reality it is hyperbolic, and therefore it's minus, and that's why we don't have imaginary time. So if we have imaginary time, or genuinely imaginary, with relation to the real time, therefore this relation will be split complex, and therefore it will be hyperbolic, and therefore we will have minus. And this is very important because this minus will be the reason why we get the equivalence between these two sides.